Now our next aim is to prove that, is to show that the dual code, which is described in terms of the local components of a Weil differential, can be represented in terms of NAG code, which is described in terms of the evaluation of some functions at given distinct places, P with an appropriate choice of the divisor H. And indeed, we will see that this H will be in the form of the canonical divisor minus G of D, and here the canonical divisor satisfies these two properties. So indeed, I mean, for this description, indeed we can see how the duality theorem is important, because in the construction of this type of AG codes, we consider the Weil differential from this space, thanks to by the one-to-one correspondence, these two structures. And if you consider the duality theorem, which tells us this vector space can be written in terms of the Riemann-Roch space, we can see the equality of these two structures. But here's the matter is that how we can write H, and to be able to write it's this H in this form, the main question is there, I mean, does there exist a Weil differential that satisfies these two properties? And we answer this question by lemma 2 to 9, and by regarding our setting. So that means if we are given n distinct pairwise distinct places, we can guarantee the existence of a Weil differential that satisfies these two properties. So that means it has poles at this given distinct places of order 1, and its local components at pi's of 1 is equal to 1. And here in its proof, we use two main steps which appears in the proof of the weak approximation theorem. But before that, first, let me consider an arbitrary Weil differential. Because we know that Weil differential space is an additive for any function field. And if we look at its valuation at pi, we know that this is an integer. And by this integer and with the setting, here we can use the weak approximation theorem to be able to choose a function z whose zeros and poles at pi's, I mean the pole orders or the zero orders are described, can be described in terms of the poles and the zeros of this omega 0 minus 1. So that can be described as given integers. And by setting a new Weil differential, which will be a product of this function with this property and this Weil differential omega 0, we obtain its valuations as -1 because VPI of omega star is VPI of Z plus VPI of omega 0, and with the choice of Z, we see that V star satisfies, valuations of V star satisfies this property. So that means they have poles at PIs of order 1. On the other hand, or moreover, we can also observe that this Weil differential has local components at Pi of 1 as non-zero elements in the base field in the FQ, because since VPI of since we have the characterization for the Weil differentials that might have poles or zeros of order 1 at PIs, we know that if it has no poles, the local component of 1 is going to be 0. So if we take the contrapositive, that means VPI of omega 0 is -1. So that means this is the case. We know that this local component is going to be non-zero. And since, thanks to this observation and thanks to this characterization, we can conclude that this local component of 1 is non-zero. And again, by the weak approximation theorem, in this case, we can guarantee the existence of a function y such that VPI of y minus ai is strictly positive. So that means y minus ai lies in the places pi's, and since ai's are the elements from FQ and the constant field has always trivial intersections with only 0 intersections with the places, and this tells us y of pi is equal to ai. And moreover, if ai's are non-zero, so that means y has no 0, or so if it is non-zero or if it is not infinity, so that means y has no poles or zeros at pi, so that means its valuation at pi is also 0. And again, thanks to this choice, now we set a Weil differential in terms of its inverse, in terms of a Weil differential, which is described as the multiplication of the inverse of this y times omega star, and we obtain VPI of omega as VPI of y inverse plus VPI of little star. If VPI of y is 0, this is going to be 0, and we know that VPI of omega star is -1. This also shows that VPI of omega is -1. And if we are able to see that its local component, so remains to show that if its local component of 1 is equal to 1, we can see the existence of such a Weil differential. And in order to see that, just let me simply write the first definition of a local component of Weil differential. Indeed, this is a Weil differential of the local adile. At pi's component, we have only one, and the other components are going to be 0. And since we set omega as y inverse omega star, and again, by the definition of this multiplication by f, and thanks to the ring structure of the adile space, that means this is going to be Weil differential V star of the adile, local adile iota pi of y inverse. And again, by the definition of a local component, indeed, we can see that this is a local component V star at pi of y inverse. And since, let me again recall one of our claim that we consider in our lecture. If we have a function which has no pose at pi, and if we have a Weil differential that might have pole of order at most 1, we know that this local component can be written as x of p time local component of 1. And thanks to this equality, we can write this statement as y inverse pi times v star pi of 1. And since we set this quantity as ai, and since this is also something we will discuss in the discussion session, can be written as A inverse, indeed, we can see the desired equality. And maybe as a hint, in order to see this equality, let me remind you how we choose the function y by weak approximation theorem. So that means y of pi is equal to ai, and y inverse pi can be written as 1 over 1 of pi, but 1 of pi is obviously 1, and y of pi, and since we had y of pi as ai, indeed we can see that this is just A inverse. And indeed, this proposition shows us the existence of such a Weil differential. And thanks to the existence of such a Weil differential, now we can describe AG code C omega d of G in terms of an AG code which is derived from the evaluations of the functions from the Riemann space of G.